All right, we're back again for physics. My name's Isaac, and I'm a tutor here at CWI. Today we're going to discuss briefly units. Hopefully you've gotten a chance to see Ahab's lecture on units. I think he does a fine job of explaining their origins and why they exist. But for me, I'm just going to kind of skip that good part, let Ahab do that, and just discuss about units in a little bit more of a direct way. So there's really two world systems of units that are still used today. The most popular one is the SI units, that stands in French for System International Units. And what it is this is essentially, this is the metric system, right? Everything's in base 10, and we'll discuss that a little bit later in the video. Then we have the imperial system. Well, that's a system that we use in the United States. There's a joke that there's two kinds of countries, those that use the metric system and those that have gone to the moon. And so that would be us. We went to the moon with the imperial system, but also we built a Mars probe. I don't quite remember when, but it was a NASA project. And some of the contractors were working in different unit systems. You know, NASA was working in SI, one of their contractors was working in Imperial, and so they launched this probe to Mars, and it's like a 6 to 9 month journey to get there. So everybody's waiting. You know, there's two things that are so important. Then is the takeoff. Takeoff went smooth, and then when you get there, the landing is super important. So 9 months, 6 months, I forget how long it took, maybe even more than that. This thing is going to Mars, and then it gets into the Martian atmosphere, and they lose its signal, and they're just not quite sure what happened for a while. Well, it turns out that the contractors, because they used Imperial and because NASA used SI, there was a mistake in conversion, and the parachute never opened. So the parachute was supposed to open at a certain height to slow the descent of the probe, and that never happened because of the fact that the world has two different unit systems, and ever since then, NASA says no Imperial system. We don't work with Imperial contractors. But most likely you're an engineer. I mean, obviously some of you are going to be scientists and maybe even math people, and who knows, maybe even chemists or geoscientists. But I'm guessing most of you are going to be engineers. So I'm in science, I'm in physics, and one of the reasons why I did that is because of SI units in the metric system. I can work with imperial units, but I really don't like to. They're kind of inconvenient. But as an engineer in the United States, you're definitely going to use the imperial system and the SI system quite a bit. And so as you get into later classes like statics, you're going to have problems with imperial and SI. But the beautiful thing is that in this class, we use SI units. This is purely a physics course. So SI units, there's three really important ones. There's a couple more necessary ones. You know, there's kind of this fundamental amount of units, and with that fundamental amount of units, you can describe every other odd unit that exists in science. But the three basic ones that we're going to be looking at the most, we're going to start with the kilogram. And this is kind of interesting because, of course, the kilogram isn't the base unit in the metric system. The base unit is gram. But a gram's a pretty small amount, so they decided to make the kilogram your standard mass, right? So this is a unit of mass. And right off the bat, let's get this out of the way. Mass and weight are not the same thing. So, and you'll learn this later on, but I want to just let you know now to not confuse mass and weight. So mass is something, like I have mass, right? I have the same mass here on Earth than if I was in deep space. My mass is a constant. Of course, I'm, accumulating and losing mass all the time through eating and other processes. But my mass is more or less like at any given instant. It doesn't matter whether I'm on Earth or on Mars or on the Moon or in interstellar space. My mass it's an amount of stuff. Whereas my weight is how much that mass is being pushed down due to gravity. So when I step on a scale, that's a weight. So pounds, for example, pounds in the imperial system, pounds is a weight, not a mass. So pounds and kilograms are not equivalent because kilograms are a mass and pounds are a weight. And a weight is a force. It's the force of gravity acting on your mass. So we get that out of the way now. It'll make a little bit more sense later. But you can think about mass as, like it's each atom in our body has some intrinsic mass to it. Each subatomic particle has some mass to it. And so it doesn't matter where those particles are at, they're going to have the same mass. So that's the kilogram. And of course, kilo is metric for 1,000. Hopefully you've got a good grasp on the metric system. If not, I recommend looking into it quite a bit and feeling very comfortable with it before you move on. So there's the kilogram. That's one of the essential units that we're going to use in this physics course. Then there is the meter. And of course the meter is the metric base, right? Meter. You could say kilometers or decimeters or whatever, micrometers, nanometers, but the base unit in the metric system is a meter. And a meter is a little bit over a yard. If you're just like trying to estimate things, just think of it as just a tad bit bigger than a yard. And so a meter is a unit of distance. And remember from last video, distance and displacement are different things. So when we say meters, like if we say 4 meters, that just means I've got a 4 meter sphere around me. I know it's 4 meters from where I'm at, right? But I don't know in which direction. So that would be a scalar. A meter is a scalar, but if I say 4 meters, let's say north, 4 meters north, that's now a displacement. It's a distance with a direction. So this is a unit of distance. It's crucial. And then of course, so we have mass, distance, we need time. So time is in seconds. This is something that everybody agrees on. Everybody agrees on seconds. And if I remember correctly, it's from the Babylonians, and that's why if we have a weird base system, there seems to be a lot of 6s that show up in our time units, like 60 seconds in a minute, 60 minutes in an hour, and then for some reason 24 hours in a day. That was probably just a fudge factor later on. But yeah, it is interesting to have a system because, of course, metric is base 10. Well, seconds are actually, I guess you can consider them base 60 to some extent. So unit of time, and there are many other units that we will see in this class, but they can all be defined as some combination of these units. Just to give an example, force is kilogram meters per second squared. That's a force. Or if you wanted to do momentum, that is a kilogram meter per second. And so, as you can see, we can define all of these other very important units in terms of these 3 base units. And there's a few more base units that show up to help us deal with electricity and magnetism, but this class is more about the more physical, gravity, motion, inertia, kind of the very, very Newtonian things in physics. And so these are the 3 units that we really need. And I hope this video is helpful. And I'll see you next time to talk about how we can use some of these units when we're talking about vectors. All right, I hope you have a great day. I hope this was helpful, and I'll see you next video.